Organic photovoltaic cells, materials, technologies, and performance. Organic photovoltaic, OPV, cells have emerged as a promising class of third-generation solar energy technologies due to their potential for low-cost manufacturing, mechanical flexibility, and tunable optoelectronic properties. This video presents a comprehensive scientific assessment of OPV cells, including their historical evolution, material systems, device architectures, working principles, and performance characteristics. Comparisons with conventional photovoltaic (PV) technologies are provided to contextualize their advantages and limitations. Recent advances in organic semiconductors, device engineering, and fabrication techniques have enabled power conversion efficiencies (PCEs) approaching approximately 18 to 20%, although challenges related to long-term stability and scalability remain. Future research directions emphasize material innovation, morphology control, and device optimization to enhance efficiency and durability, positioning OPVs as viable candidates for next-generation renewable energy systems. Photovoltaic (PV) technologies convert solar radiation into electricity via the photovoltaic effect, wherein incident photons generate charge carriers in semiconducting materials. Conventional PV devices are predominantly based on crystalline silicon, offering high efficiencies and long-term stability but at relatively high manufacturing costs. In contrast, organic photovoltaic, OPV, cells use carbon-based semiconductors, such as conjugated polymers and small molecules, enabling lightweight, flexible, and solution-processable devices. Although OPVs have historically exhibited lower efficiencies and shorter operational lifetimes than inorganic counterparts, continuous advancements in materials chemistry and device engineering have significantly improved their performance. Their compatibility with roll-to-roll processing and potential for semi-transparent and flexible applications make them attractive for emerging technologies such as wearable electronics and building-integrated photovoltaics. Evolution of photovoltaic technologies. Historical development. The photovoltaic effect was first reported by Alexandre Edmond Becquerel in 1839, marking the origin of solar energy research. Early developments included selenium-based devices by Charles Fritts with efficiencies near 1%. Significant progress occurred during the mid-20th century, with silicon-based solar cells achieving efficiencies above 10%, driven largely by space applications. The oil crises of the 1970s accelerated research into alternative energy sources, leading to the development of thin film and emerging photovoltaic technologies. In the 21st century, advanced materials such as perovskites, quantum dots, and organic semiconductors have expanded the scope of PV research, with efficiencies exceeding 25% in certain systems. Organic photovoltaics originated from early studies on photoconductive polymers, with substantial progress achieved in the 1990s through the development of conjugated polymers and fullerene derivatives. Initial efficiencies below 1% have increased to nearly 20% in modern OPV systems through innovations in donor acceptor materials and device architectures. Generations of photovoltaic technologies. Photovoltaic technologies are commonly categorized into three generations. First-generation cells are based on crystalline silicon and exhibit efficiencies up to approximately 25%, but involve high material and processing costs. Second-generation technologies, including thin-film cells such as cadmium tellurium, CDT, and SiGs, offer reduced material usage and improved flexibility, albeit with moderate efficiencies, approximately 10 to 15%. Third-generation technologies, including OPVs, perovskites, and dye-sensitized solar cells, aim to achieve high efficiency at lower cost through novel materials and architectures. Materials and device technologies. Classification of photovoltaic materials. PV cells can be broadly classified based on material composition. Silicon-based devices dominate the market due to their maturity and reliability. Thin-film technologies reduce material consumption and enable flexible designs. Dye-sensitized and organic solar cells provide low-cost alternatives with tunable optical properties, while multi-junction and concentrator systems achieve record efficiencies exceeding 40% under specialized conditions. Organic semiconducting materials. The active layer in OPV devices consists of a blend of electron donor and electron acceptor materials forming a bulk heterojunction. Donor materials typically include conjugated polymers such as poly,3-hexylthiophene, P3HT, and advanced donor acceptor copolymers, for instance, PM6, PTB7TH. Acceptors initially relied on fullerene derivatives such as 6,6-phenyl butyric acid methyl ester, PCBM, but recent advances have shifted toward non-fullerene acceptors, NFAs, like ITIC and Y6, which offer improved absorption and tunable energy levels. The performance of OPVs is strongly influenced by molecular design, energy level alignment, absorption spectrum, and nanoscale morphology. Rational design of donor acceptor systems enables efficient exciton dissociation and charge transport. Electrodes and interfaces. Transparent conductive electrodes such as indium tin oxide, ETO, or fluorine-doped tin oxide, FTO, are commonly used as anodes, while low work function metals such as aluminum or silver serve as cathodes. Interface engineering using hole and electron transport layers, for example, PEDOT-PSS, zinc oxide, improves charge extraction and reduces recombination losses. Encapsulation materials. Encapsulation is critical for OPV stability due to the sensitivity of organic materials to oxygen and moisture. Barrier materials include glass, polymer films, for example, PET, PEN, and inorganic coatings, such as CO2, titanium 4 oxide. Flexible encapsulation strategies are particularly important for wearable and portable applications. Working principles of OPV cells. Light absorption and exciton generation. Upon illumination, organic semiconductors absorb photons, generating excitons, bound electron hole pairs. Conjugated polymers with extended pi electron systems enhance absorption in the visible and near-infrared regions. Charge separation. Excitons diffuse to donor acceptor interfaces, where energy level offsets facilitate their dissociation into free charge carriers. Efficient charge separation requires optimized morphology and nanoscale phase separation. Charge transport and collection. Electrons and holes are transported through acceptor and donor domains, respectively, toward the electrodes. Charge mobility, energy level alignment, and interfacial engineering play crucial roles in minimizing recombination losses. Electrical output. Device performance is quantified using parameters such as short circuit current density, JSC, open circuit voltage, VARC, fill factor, FF, and power conversion efficiency, PCE. These parameters collectively determine the efficiency of solar energy conversion. Device architectures. OPV devices have evolved through several structural configurations: single-layer devices, simple architecture but limited efficiency; bilayer heterojunctions, improved charge separation but limited interfacial area; bulk heterojunctions, BHJ, interpenetrating donor acceptor networks enabling efficient exciton dissociation and charge transport, widely used in high-performance OPVs; tandem cells, multi-junction architectures that absorb complementary spectral regions, achieving higher efficiencies. Performance and efficiency. The performance of OPV cells has improved significantly over the past 2 decades. According to reports from the National Renewable Energy Laboratory, NREL, modern OPVs achieve PCE values approaching approximately 18 to 20%, with fill factors exceeding 80% in optimized systems. Literature reports indicate PCE values up to 18.6% and average efficiencies around 13 to 14%. Despite these advancements, OPVs still lag behind silicon and multi-junction technologies in absolute efficiency. However, their advantages in low-light performance, flexibility, and manufacturing scalability provide unique application opportunities. Evaluation and future prospects. OPV technology offers several advantages, including low-cost fabrication via solution processing, mechanical flexibility, lightweight design, and tunable optical properties. These features enable applications in flexible electronics, wearable devices, and semi-transparent photovoltaic windows. However, challenges remain, particularly in terms of operational stability, degradation under environmental conditions, and relatively lower efficiency compared to inorganic technologies. Trade-offs between transparency and efficiency further complicate device optimization in applications such as building integrated photovoltaics. Recent developments in transparent OPVs have demonstrated promising performance, with average visible transmittance exceeding 40% and improved light utilization efficiency. Advances in non-fullerene acceptors, tandem architectures, and morphology control are expected to further enhance device performance. Future research should focus on improving intrinsic material stability, understanding degradation mechanisms, and developing scalable manufacturing processes. Collaborative efforts between academia, industry, and policymakers will be essential to accelerate commercialization. In conclusion, organic photovoltaic cells represent a rapidly evolving class of solar energy technologies with significant potential for sustainable and versatile energy generation. While current limitations in efficiency and stability hinder widespread commercialization, ongoing advancements in materials science and device engineering continue to close the performance gap with conventional technologies. With continued innovation, OPVs are poised to play a crucial role in the diversification of renewable energy systems, particularly in applications where flexibility, transparency, and low-cost manufacturing are essential.